So good morning students, this is Vignesh. I am taking computer architecture and organization. Before that, so what is computer architecture and computer organization? So computer architecture is concerned with the hardware components, concerned with the way hardware components. And computer organization is concerned with the structure and behavior of a computer system as seen by the user. Simply we call it as computer architecture is it involves logical components. What are the logical components? One is instruction sets, another one is addressing modes, data types, then cache optimization. The computer organization is involves physical components such as circuits, design, adders, signals, and peripherals. So this is the thing for computer architecture and computer organization. So next, our first unit, data representation. Any computer data can be represented as data types, complements, fixed point representation, floating point representations, other binary codes, error detection codes. These are all the some uh, data representation we support any computers. First we shall go to see data types in next slide. So data means it is a information. Any computer is dealing with data and data elements, then program or instructions. So data means it is two types. One is numeric data, another one is non-numeric data. Numeric for integers and real numbers, non-numeric for letters or symbols. So the next one is data elements. In data elements it can be supported for data structures. The data structures, the structure of data is call it as linear list, trees, then rings, etc. Go to next slide for detailed explanation of numeric data. That is the numeric data. There are two types of numeric data. One is integer numbers and another one is real numbers. Then the non-numeric data is symbols or letters. Already we told you. The first one for in the data representations number system. There are two types of number systems. There are two categories, two major categories. One is non-positional, another one is positional number system. Non-positional is Roman number system. The positional number system for each digit position has a value called a weight associated with it. Sometimes the positional number system is called a weighted code because of each position has a separate weight. So what are the some positional number systems are? Binary. First one is binary, second one is octal, third one is decimal, fourth one is hexadecimal. So each positional numbers has separate bases because the binary is only two digits, that's why the base of the binary is 2. Then second one octal for 8 digits, that is 0 to 7, the base of the number is 8. The next decimal number 0 to 9, so total 10 numbers, the base is 10. Then hexadecimal is 16 numbers, so the base of the number is 16. R for base of the number, so r equal to 2 for binary, r equal to 16 for hexadecimal, the base is 16. R equal to 10 for decimal number system, r equal to 8 for octal number system. Okay, go to next slide for positional number system in the digital computers. Why we are using positional number systems for any digital computers? The major consideration is cost and time. So that's why in any digital computers we support or users can use positional number system. So first of all we shall go to binary addition table, then decimal addition table. This is binary for only two digits, zeros or one, so you can add 0 plus 0, it's coming with the answer is 0. 0 plus 1 for 1. Again 1 plus 0 for 1 in the third square, then another the last fourth square for 1 plus 1 is 1 0. So 1 0 for the binary. You will not take 2. 1 plus 1 for 2. It is for 1 plus 1 for 1 0. Next we can add 1 0 plus 1 is 1 1. Again you can add 1 for 1 1. We got the result 1 0 0. So this is the binary addition. Then decimal addition table. So decimal addition, normally you can add 0 plus 0 for 0. You can add all the 9 digits for 0. So we get the result 0 plus 1 for 1, 0 plus 2 2, 0 plus 3 for 3, 0 plus 4, and 0 plus 9 for 9. So likewise we can add all the digits. We get the addition table of decimal. We go to next. This is our representation of all the 4 numbers. First one for decimal. So totally 15 decimal numbers. Each 15 decimal numbers which is represented as 4-bit binary form, starting from 0 0 0 for 0, 15 for 1 1 1. So this is the 4-bit binary form. Then octal can be represented as 0 to 7. The next 8 and 9 are skip. Then the next number will come 1 0 1 1 1 2 1 3 1 4 1 5 1 6 1 1 7. Then hexadecimal number 0 to 9 is common for decimal number. Then 10 is A, 11 is B, 12 is C, 13 is D, 14 is E, 15 for F. So this is the representation of all the positional numbers. Okay, go to next. This is our conversion for bases. Conversion means one base to another base, that is one base for decimal number. We can convert other base for binary or octal or hexadecimal. So these are all some rules for applying conversions. There are several rules are there. First we separate the number into its integer. Suppose our given number is integer part and fractional part. There are two parts. One, for example, 736.4. Here there are two parts. One is integer part, another one is a fractional part. First we can take integer part for converting the bases. After that we can take integer real part for converting its bases. So this is the rule we shall apply. Next page. So this is our example. Convert 41.6875, which is the decimal number. There are two parts. One is integer part, another one is a real part for converting base 2. So first we'll take integer part for 41. 41 is divided by 2 because of I'm converting the base 2, so that's why I'm divided by we take 2. So 41, how many times 41 is divided by 2? That is 20 times. 22s are 40. So we get the remainder is 1. Again we can divide by 2 for 20. So 10 times 10 2s are 20. So remainder is 0. Then 5 2s are 10. The remainder is 0. Then 2 2s are 4. Remainder is 1. Then 1 2s are 2. Remainder is 0. Again we can divide by 2. We get 0 1. Now we can take all the remainders for bottom to top. So 1 0 1 0 0 1 is a binary numbers, that is a base 2. So 41 is converted to binary, that is the base 2. The next part is fractional part. We can take fractional part for 0.6875. So now we shall multiply by 2, that is 0.6875 into 2. We get the result of 1.3750. Now we take 1 is a remainder. After that 0.3750, again we multiplied by 2, so we shall get 0.7500. Now the remainder is 0. Again we can take 0.7500 multiplied by 2, then 1.500, so 1 is remainder. Again we can take 0.500 for multiplying 2, so we get 1.40. So you can take the remainder, all the remainder of top to bottom. So 0.1011. We can combine both integer part and real part. We got the result 101001.1011. This is our conversion for decimal to binary. Likewise, you can likewise there are several exercises there. You can try and verify this result. We go to next slide. This is complement of numbers. So complements means to convert positive to negative or negative to positive, vice versa. There are two types of complements. One is R's complement, another one is a R minus 1 complements. So R complements, first we take R minus 1 complements. So how to calculate the R minus 1 complement? That means each digit subtract of a number from R minus 1. Subtract each digit of a number R minus 1. For example, first we take one number for decimal 835 base 10. No doubt about this is the decimal number which is converted to 9's complement. So each digit subtract from 9. So first 9 minus 5, we get the result is 4. The 9 minus 3, we get 6. 9 minus 8, we get 1. So 164 is a 9's complement of 835 base 10. Similarly for 1's complement 1010. So here you can subtract each digit for 1. So 1 minus 1, that is 1 minus 0 is 1 first, then 1 minus 1 is 0, next 1 minus 0 is 1, the next 1 minus 1 for 0. So we get result 0 1 0 1 is a complement of ones, that is one's complement. Okay, next R's complement. Here in the R's complement we can add 1 for least significant bit, that is R least significant bit of its R minus 1 complement. First we shall get R minus 1 complement. After that we can add the least significant bit LSB. We get the result of R minus 1 complement. For example, in 835 for base 10 is, for the 9's complement is 164. Here we can add the least significant bit for 4. For adding 1 we get the result of R's complement, that is the 10's complement 165. Similarly 0101 is a 1's complement of 1010. Then we shall add 1 for R's complement, that is the result is 0110. So this is our complement numbers. So this will complete 2 topics in the data representation. Remaining topics we shall discuss about next lecture video. Thank you.